So in 2.1, you're going to finally start seeing a little bit of the beginnings of calculus. So we're going to talk about what is a limit. We're going to talk about tangent lines, secant lines, and velocity. So just remember that a tangent line is a line through a point on a curve that touches the curve just once relative to the location of the point and follows the direction of the curve at that point. So we can see here that this is called a tangent line. It is on the outside of the curve. It's touching the curve exactly at one point. Here's an example of a tangent line. Here's an example of a tangent line. Depending upon where you're at on the curve, the tangent line is going to move with the curve. So if we're over here, our tangent line looks like that. But if we're over here, the tangent line looks like that. Now, tangent lines indicate how a function is moving across time. And I may be able to show you what I mean, maybe. There's a really good little graphic. I'm just not sure if it exists somewhere. It might. Let's see if I can find it. Just a sec, I'll see if I can find the old school version. It's just very slow. Now, you may recall back in geometry and even from trigonometry, we talked about something called a secant. Well, in a calculus sort of environment, a secant is just the connection of any 2 points along the curve. I'm trying to see if I have that graphic because it's so pretty. It might not exist anymore. I'll look for it. Oh, is it down there? Nope, it's not down there. Anyway, so these are examples of tangent lines, but a secant line goes through a point. So if I wanted a secant line between these 2 points on the graph, I just connect them. So you have to know the language. So it's important to know that a tangent line is a line through a point on a curve that touches the curve just once relative to its location. So we only have one point we're taking into consideration. But if you look down here, a secant line is a line between any 2 points on a function. A secant can be used to find a tangent, but what we're going to have to do is we're going to have to get a secant line that gets closer and closer and closer to approximating our tangent line. Some other words from geometry that might be helpful: radius, diameter, and chord. So a chord is a connection of any 2 points on the circle. So if you think about a secant line, is just an extension of any chord. The diameter goes perfectly through the center, and the radius is half of that distance. So tangent lines hit the curve once relative to that particular location. Secant lines are 2 points on the curve that we connect. So there is a difference. And we're going to be using calculus to talk about the tangents slope, the secant slope, and how that can be interpreted. I wish I could find the thing I'm looking for. Let's see. Oh, it's in my old stuff. I just got to remember where. Maybe it's there. Did I find it? Oh, I found it. I'm so excited. Okay. So for a moment, let's just look at this curve, okay? So let's look at this tangent line. So the tangent line's moving across the curve, okay? What do you notice is happening when our function is increasing from left to right? What color is our tangent line? It's green. What would the slopes of those lines be when it's green? They would be positive, right? So as our function is increasing, the slopes of the tangent are positive and our line turns green. Okay, so now let's look at where our function is decreasing when the line is red. So when the tangent line follows the curve and the curve is going downhill, what do you notice about all the tangents? They're red and they have negative slopes. What happens when we hit a peak or a valley, those local extrema we learned about last year? What happens to the tangent line's color? It turns black. And at that particular point, that is where the tangent line is horizontal. So what would the slope be then? 0. So what's interesting is if we know about the slopes of the tangents, we can find out whether our function is going uphill, increasing, downhill, decreasing, or whether it has possibly a local min or max. So the tangent lines of a curve, especially curves that are complicated like this one, really are going to help us discover what the curve and function is doing. And so that is something we're really going to be looking at as we go through this stuff. Okay, so let me get this off of the screen, hopefully. I was glad I found it though. Okay. Everybody have those definitions down there? Okay. So here's where I was just kind of showing you that when a function is, or when a function has a local min or max, the tangent line is horizontal. When the function is increasing, the tangent lines are positive. When a function is decreasing, the tangent lines are negative. So just a little graphic there, since I couldn't put the actual physical graphic in there for you. So some things to remember: that a slope of a tangent will be the slope of the line when A is our point of interest and X gets closer and closer and closer to it. So it is f of x minus f of a over x minus a. Now, the slope of a tangent, you have to remember this word here. It is an instantaneous rate of change. So calculus was invented, discovered, found, I don't know, however you want to describe it. Newton, when he was looking for some formulas that would go along with some physics applications, he was looking at rates of movement. And that instantaneous rate of change is a very important concept that before calculus, we had to kind of do some manual things that you're going to see at the beginning of this chapter. And as we inch toward chapter 3, you will find the formulas of calculus that allow us to do some of this stuff much quicker than we did in chapter 2. So some of the stuff we do in chapter 2 is going to be extended. And when we get to chapter 3, we'll be like, oh, Mrs. Hott, why didn't you show me those formulas? Well, I can't. We gotta learn to walk a little bit before we learn to run. So we'll start out finding the slopes of our tangent lines, getting those A and those X's closer and closer together until they're almost like that instant we hit A. And remember, you have to know instantaneous rate of change refers to the slope of a tangent. You have to get that memorized into your brain, okay? And then just like anything, think about our equation of any line is just y minus y1 equals m times the quantity of x minus x1. That's what that is. It's just referring to, there's the slope of the tangent, and here is the point that you are approaching. Don't make that harder than it is. It is really just y minus y1 equals m times x minus x1. What are they doing? They're using function notation. They are saying, oh, we are at the point a f of a, which is just the point at a. See, our point a f of a, okay? Now a secant line, the only difference is we are not getting closer to some particular point A that we have found. So you'll notice if they ask you to find the slope of a secant, they're going to give you 2 points. So it's going to feel like a traditional slope from back in algebra class. So you'll notice here we have point x1, and the point x1 would be f of x1 would be your y, and then x2. So that's the kind of the way to discover which one are they giving me. If they ask instantaneous rate of change at a point, they're only going to give you 1 point. Or if they say a slope of a tangent, they're only going to give you 1 point. If they say a slope of a secant, they are going to have chosen 2 points in time or 2 x values. So that's usually the difference. So if they say instantaneous rate of change, they'll give you 1 point. If they say average rate of change, they're going to give you 2 points. And so just recognize that a slope of a tangent is referring to 1 point on the graph. A slope of a secant is between 2 particular points on the graph. And so if you kind of keep that in your head, that will help you through this process. Slope of the tangent is at a point. Slope of a secant is at 2 points. So just kind of remember that as we go through it. It's same old slope formula for both. Same old y minus y1 equals m times the quantity of x minus x1 for both if we wanted to find a secant line. Those formulas are not different. What's different is how we approach them, okay? So let's look at an example. It says find the slope in the equation of the tangent line of f of x equals x squared through the point 2, 4. Now, if you were doing this by hand, can I see what your graph looks like? Okay, so what I want you to do on your paper, you have the parabola. I want you to do your very best to kind of skim across the graph, hitting the point 2, 4. So if your point 2, 4 isn't highlighted, make a dot there at 2, 4, and then do your very best to guesstimate how you would skim across the graph nicely. Now, mine is the exact tangent line because I know how to find that. But for now, for you, guesstimate, get your graph as quick as you can. Okay. Now, how could we do this? Well, there is a mixture of ways that we can go about finding this, but this is what I want you to do, okay? So our A value is 2. So, you know, obviously f of A is just f of 2, or 2 squared is 4. So that's where they got the point 2, 4. Okay. Now, we want to choose an x value that is super close to it. Now, this is only a guesstimate of what the slope is going to be. So a value that's close to 2, let's go with 1.9. I don't know. Just we'll go 1/10 away. You could go 2.1 or 1.9. Don't care. Okay. So the slope of a tangent line is going to be f of x minus f of a. And I'm going to put a little t there to kind of distinguish that it's a tangent slope I'm looking for, over x minus a. Now, we already know our a is 2. Our x needs to be something. Remember, if you looked back at the definition on the page before, the definition says that as x gets close to 2. So let's make our x 1.9. Now, again, you could go a little bit over, a little bit under, don't care, pick one. And if you square 1.9, f of x is just f of 1.9. And 1.9 squared is 3.61. Okay. Now it can be, like I said, it can be 1/10. The more you get closer to that value, thank you. The closer you get to that value, the better it is. So we would be more accurate if we were 1.99 or 1.999. The more close, the better. So let's plug our values in. F of x is 3.61. F of a is 4. X is 1.9. A is 2. 3.61 minus 4 is negative 0.39. 1.9 minus 2 is negative 0.1. If we do those two negatives, are going to make a positive. 0.39 divided by 0.1 is about 3.9. Now, that means the slope of the tangent means that it's going to be super, super close to 3.9. Now, what's a number that is super close to 3.9? 4. So odds are, if we knew the exact formula like Mrs. Hott does, we would find that the slope is 4. Now look at my graph for a moment. If we find 2 points on this line and we go up 4 over 1, oh my goodness gracious, we found the slope of the tangent. The slope of the tangent is 4. Now it says to find the slope of the tangent and the equation of the tangent line. So remember, y minus f of a equals m times x minus a. Now, what is that? Well, that's just y minus y1 equals m times x minus x1. Our point is 2, 4. Our slope is 4. Don't do anything funky. It is what we always knew it was. So it's going to be y minus 4 equals 4 times the quantity of x minus 2. So, you know, I'm okay with you leaving it there. Most of the time, finding an equation of any line in slope-intercept form is slightly more helpful. If we distribute the 4, we get 4x minus 8. Add 4 to both sides, we get 4x minus 4. Look at our line. Now, this is the exact one because I knew how to find the exact one. It has a y-intercept of negative 4. Slope is 4, up 4 over 1, up 4 over 1, up 4 over 1. You know, you get it. So we have found the slope of the tangent line. Most of the time, for now, you are going to get a guesstimate. Round it to the nearest most of the time is going to be a good rule of thumb while we're doing this process until we know the exact formula. We don't know the exact formula yet. We're going to get there. But for now, you may have to draw it and guesstimate, oh, it looks like it's about 4. You know, it usually comes out to be a decent number, okay? Now let's look at the difference between our first example, 1A and 1B. Do you see how in 1A they only gave us 1 point, the 0.24? But in 1B, they gave us 2 points because they wanted the slope of a secant. So a slope of a secant line is the connection of those 2 points along the curve. It's just like any line we know, okay? So let's think about what the difference is. A slope of a secant is just a normal slope, f of x2 minus f of x1 over x2 minus x1. In this particular case, I'm going to call x1, 1. So if we're using that same curve, f of x equals x squared again, which we are, then f of x1 is 1, and then x2 is 2. So f of x2 is 2 squared or 4. So we're just going to use the points 1, 1 and 2, 4. And we're going to find the slope of the line between those 2 points. So we're back in algebra class. It shouldn't be anything more difficult than what it is. And so what we're going to do is first find the slope. So our slope is going to be 4 minus 1 over 2 minus, not that, 2 minus 1. Like that's not going to work. Which is 3 over 1 or 3. And then you can either use the 0.11 or 2,4, doesn't matter. It'll get you to the same place. Y minus 1 equals 3 times x minus 1. And then I can make it prettier, but technically if you just leave it at this point, I'm okay. That is the equation. And I know hopefully by now you can do algebra. So, but if we check the line over here, it has a y-intercept of negative 2, went up 3 over 1, up 3 over 1, up 3 over 1. The slope of the secant is just the connection of any 2 points along our curve. So it is different than a slope of a tangent. A slope of a tangent, we have to choose the second point because we only are given one that's super close. So I usually do a tenth. Usually a tenth gives me enough information to guesstimate what's happening. Any questions about our first example? Does that look good? Okay. So in this example, it says estimate the slope of the tangent when x is 1 using a table, and then we're going to find the equation of the tangent line at the point that was given. So if x is 1 and our equation is f of x equals 2x squared, you'll notice I've already told you that f of x is 2. 2 times 1 squared is 2, last I checked. What we're going to do is we are going to get super close, okay? So first, let's do the 1/10 away. Okay, so we're going to do these two. So if we do 2 times 1.1 squared, we get 2.42. If we get 2 times 0.9 squared, we get 1.62. So now let's do 1.01. So now we're only 100th away. So 2 times 1.01 squared is 2.0402. And then 2 times 0.99 squared is 1.9602. Now, I don't care, I don't want to do this a million times, so let's just do the slope between, oh, let's not do this one, I'm sorry. Let's do the slope between the closest ones. So let's skip that one and that one. And let's just calculate the slope as we get closer from the right side and closer from the left side to guesstimate what our slope really is. Now, I already know what the slope is, just because I know a shortcut that you don't know. Let's go ahead and find it. Okay, so the slope of our tangent, let's do it with this one. So we already have our point, and we have the original point, 1, 2. And so it's just f of x minus f of a over x minus a. Okay, so 2.0402 minus 2 is 0.0402, and then 1.01 minus 1 is 0.01, and you divide that by 0.01, and you get 4.02. So what is it looking like our slope of our tangent is? 4. So it looks as if it's going to be 4. But let's do it now on the other side. And so this one, you'll notice the slope is just a teeny touch above 4. And then on the other side, bet you it's going to be just a teeny tiny bit under 4. So it might be like 3.99. But let's do it. Okay. So the slope of the tangent, let's do it again. This time we're going to use this point. And so it's going to be 1.9602 minus 2 over 0.99 minus 1. And you get negative 0.0398 over negative 0.1, which is approximately 3.98. So if on one side, as we're getting closer to it, we get a slope just above 4, and on the other side, we get a slope just below 4. So let me fill them in. That tells us that the slope of our tangent should be 4. Okay. The equation, let me write it down for you, is f of x minus f of a over x minus a. The a f of a is the point we are checking. We want to know the slope at 1, 2. So that's why you'll notice that 1, 2 was used in both times. So this is the point that is, the x is the thing that's getting scooching closer and closer to it. So the x and the f of x might change if we're testing something close on the left side or close on the right side. It's nice until we know the formula to do it in both directions so that we can really verify that, oh yeah, they're both getting close to 4. If we were to graph it, let me show you, do we have Desmos here? So if we look at the graph of 2x squared was our function. Now, what you can do is kind of trick Desmos to check it for you. You can do y minus 2 equals, our slope we think is 4, times the quantity of x minus 1. So let's look at what we've got there. We've got the 0.12. The slope we believe is 4. Does it touch that point where we want? Bam. Does it appear to skim across it without really touching it? If we zoom in, the closer we zoom in, we are still never, we're just skimming across the graph at that point. Okay? Okay, let's keep going. We just have 2 more examples. So here is a formula. It's based upon a real equation. Suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto. It's 450 meters above the ground. Find the velocity of the ball after 5 seconds. So if you ever see a physics problem, you may recall that the acceleration of gravity in meters per second squared is 9.8 meters per second squared. 4.9 divided by 2 is, 4.9 is 9.8 divided by 2. That is not a coincidence. That does kind of happen through the formula. But if we wanted to know the velocity after 5 seconds, do you notice how they only gave us one time, 5 seconds? So that tells us we're looking for an instantaneous velocity. Okay, so let's just, for time's sake, on your homework, I want you to do it even closer, but I don't care. Let's not do those ones. Let's just do the closer ones. So let's just, wait, let me cross. So I'm not worried about these ones. Let's just do the ones that are as close as possible. So I plugged in 5 into my formula, and I got 122.5. So that's the point that I'm touching along the curve, okay? So then let's plug in our, not those. Let's make this one 4.01. No, I'm sorry. Gosh darn it. Wait a second. It should be 5.01 and 5.1. And this one should be 4.99 and 4.9. We got to get super close to it. One is way too far away. I think I copied and pasted the values from the last slide and forgot to change those. Anyway, okay. So I'm only going to use 5.01 and 4.99. I'm going to get super close. So remember our formula for the acceleration here. S of t is a common one that they're going to use, but I'll make it x's so that we got it. Okay. So if I plug in 5.01, so let's do that. 4.9 times 5.01 squared is 122.99. 4.9 times 4.99 squared is 122.01. Okay. So let's find the slope for both of those. So let's do this one. So the slope for our first tangent is going to be 122.99 minus 122.5 over 5.01 minus 5. So this is the point that's close to what we want. This is the point we are looking at, okay? So 122.99 minus 122.5 is 0.49. And then 5.01 is 0.1 higher than 5. And if we divide it, we get 4.9. Okay, so that's our first one. What is that super close to? Isn't that, it's pretty close to 5. Okay, so let's do it again. Okay, so we're going to do 122.01 minus 122.5 over 4.99 minus 5. So we get negative 0.01 on the bottom. And we get negative 0.49. I didn't move my decimal place. I'm like, wait a second, Mrs. Hott, you don't know how to divide. This decimal place, if we divide by 100th, what happens? How many places do I have to move it? I have to move it 2 places. I didn't. I'm sorry, that's 49. And then the bottom one here, this is also 49. So that should be super close to 49. It isn't even 50. It is actually super close to 49, the real thing. So our slope of our tangent, we can guesstimate, is 49. So if you get the same one from both sides, I wouldn't even bother rounding it. That would be an indication, especially we were 100th away, which is so super close. Actually, if I would have kept the decimals going, the top one is like 49.01. The bottom one is like 48.99. You know, it's super close to 49. Okay. We're going to do one more. It says, if an arrow is shot upward on the moon with a velocity of 58 meters per second, its height in meters after t seconds is given by that height equation we see there. Let's find the average velocity over the given time intervals, and then we're going to find the instantaneous velocity. Now remember, an average velocity, that is a slope of a secant, which is just our normal slope formula, y2 minus y1 over x2 minus x1. And instantaneous velocity is a slope of a tangent. So we have to get super close to our point. So we're going to do f of x minus f of a over x minus a. Okay. Now let's start with a here. Our points, that is an interval. So this is x1 and this is x2. Okay, that is our 2 points. So our height at 1 and our height at 2, let's check. If we plug in 1, we get 58 minus 0.83 is 57.17. I'm going to keep those decimals out a little bit. If I plug in 2, 58 times 2 minus 0.83 times 4 is 112.68. So the average velocity over that interval is the slope of my secant over that interval. I just do the slope formula between those 2 points. Yes? No, be careful with that. Because of the way that formula is written, it is the value 0.83 times your time squared. So do your time squared first, following that PEMDAS. Please excuse my dear Aunt Sally. Get that value, square it, and then multiply by 0.83 so you don't mess that up. Good question. Okay, so 112.68. So our slope of our secant is 112.68 minus 57.17 over 2 minus 1. Simple slope formula, just like we've done in the past. So 112.68 minus 57.17 is 55.51. Divided by 2 is 55.51. Now that's the average velocity. Our length is meters. Our time is seconds. So that would be meters per second. Okay, now we're going to do it one more time for part B. We already know h of 1 is 57.17. And now we do h of 1.01. So 1.01, 58 times 1.01 minus 0.83 times 1.01 squared is, I'm going to go out 3 decimal places, 57.733. Okay, so that slope of that secant, so that's an average velocity just between 1 second and 1.01 seconds. We're just going to do 57.733 over minus 57.17. Doing good today. And then 1.01 minus 1. Okay, let me tell you what you get. So you get about 56.3 meters per second. Okay, so those are the slope of the secants. Oh my goodness, the sleeps. Anyway, so part B asks us to find the instantaneous velocity after 1 second. Which one of those intervals closely will match with an instantaneous velocity or a slope of a tangent? B, the second number. We've already done the work, so our slope of our tangent, with the estimate, let's just make it 56 meters per second. Now, the real answer, if we were to do it, if you knew the formula, which you don't yet, but you do know, is 56.34 is the exact answer, just because I know it. But that's a great estimate. Look how close we were. Here, let's make it 56.3. By using that interval where they were super close. Okay. Now, your homework is just those 2 problems you see there. So there you go. Do your thing. And we'll continue this eventually.